All right, chemists, let's get started. Hopefully everyone had a nice, relaxing break. We just have like a little bit more here, a sprint to the end. I think we only have 4 more classes. Yeah, 4 more lectures. All right, it's like looking into the sunset. Like we know it's gonna end. So let's just enjoy the time that we have together, all right? So a couple of announcements before I get started with chapter 10 here. I do plan on having the final exam Zoom midterm crazy session. I decided for it to be on reading day, so Thursday next week. It'll be in this room and on Zoom December 8th. So if you don't know what reading day is, basically the last day of classes is Wednesday. Like that's the last day of lecture. Finals do not start until Friday. So basically everyone gets 1 day of like no finals off, right? And then I think your guys' final exam isn't until Monday the next week. And so doing it this way allows, me to reach more people. So we'll do the review on Thursday. I'll record it, all that stuff. It's on our course calendar on Carmen. I just haven't made the documents and stuff yet, so I haven't made the page. You may be wondering, when am I going to post, or like what final exam materials will you get? So in the coming days, do expect 1 practice midterm from the department, like a Carmen one, like one of them. Because recognize that the final exam is 105 minutes. So I think the final exam is about 50 questions. It takes a long time to write that many questions. So you're going to get 1 Carmen exam. You're going to get 2 like just cumulative packets from me. I'm not going to call them practice finals. They're just big packets that have multiple choice questions in them. So I'm not going to call it a practice exam, practice final, because I don't know the timing. It's just another resource for you. So I do plan on posting that tomorrow. I just need to write the keys for them. All right. And that'll give you plenty of time to study there for the final. Other questions I get from students are like, oh, is the final mostly focused on chapters 10 through 12? I would say it is an even distribution of questions from all 12 chapters. That's what I would say. Okay. All right, so let's continue on with chapter 10. We talked about our named gas laws, relating, pressure, volume, temperature, those properties to a gas sample. We looked at the ideal gas law and how we can't connect the idea of the mole amount, so PV equals nRT moles. Tons of ways we've worked with moles this term. So we're just bringing in this new aspect and this new way to calculate moles with PV equals nRT. Then what did we do? We talked about kinetic molecular theory and the idea that temperature of your sample will relate to the average kinetic energy of your sample. Therefore, depending on what the molar mass of or the weight of each of those particles are, will tell us the distribution of speeds of those particles. So typically we think lighter particles move faster on average, hotter particles move faster on average. So keep those ideas in mind, because how fast particles are moving and how much total kinetic energy they possess will come into play in chapter 11, and talking about the properties of effusion and diffusion. So that's where we left off, where we can relate kinetic molecular theory and those tenets, the idea that we have particles, they're moving in straight lines, they're bouncing off the walls of the container. We can actually use some of those ideas and relate them to properties we can measure. So if we look back at one of these graphs, we see that in an oxygen sample, those particles are actually moving really, really fast. So like 500 meters per second. That's super fast. So the idea here is that gases, yes, they're moving fast, but when we think about the net path that they take from one point to another, it's actually quite slow, because particles, yes, they're moving fast, but they're also hitting one another. So it takes them, they take a longer path to get, from point A to point B. And that's the idea of diffusion. If I broke a perfume bottle in the corner of the room, it would take a while for that smell to, travel towards your nose. And that's the idea of mean free path. The net time it takes for some particle to make this net distance from going to point A to point B, that the collisions slow down the actual path that is made. So that's diffusion. We've all experienced diffusion, all right? And I mentioned, like the high school locker room, and you think of the Axe body spray emanating from the men's locker room. The closer you get to it, right, there's the mean free path is smaller, so there's more smelly Axe particles entering your nose. But my feminine perspective, it wasn't Axe body spray in the women's locker room. It was Sweet Pea by Bath and Body Works, or Cool Cucumber. That's the smell that haunts me. So the idea of diffusion, yes, we've experienced it, but it's actually really hard to measure mean free path. It's very hard to measure. So instead, we think about effusion. Effusion is actually an easier thing to study. It's similar. We have in both ideas. So in diffusion, you have high concentration on one side, and you just completely remove the partition until everything becomes uniform. That's diffusion. Again, hard to measure because it's related to mean free path. Effusion is similar. You have your high concentration on one side. Instead of completely removing the partition, you just make a pinhole in the partition, so a small leak. And so the rate at which particles move from one side to the other side is actually directly related to collision rate. Anytime a particle collides with that hole, it goes on the other side. Collision rate is something we've talked about. Collision rate is the reason gases exert a pressure when they are colliding with the walls of the container. That is easier to measure. So the idea here is effusion, the rate of effusion, is related to collision rate, colliding with that pinhole, and we've already related collision rate to how fast the particles move. So basically all the trends you need to know in terms of effusion, rate of effusion, is related to RMS speed, something we've already talked about. Your particles will collide more if the temperature is high. The particles will collide more when the particles are light. So the idea here, let's go through these questions. Particle speed increases. How does collision rate with your pinhole change? Increase or decrease? I already said it. The faster the particles are moving, will they collide more or less with the pinhole? More, yes. I know you guys are tired from all your turkey and tryptophan. That's a misconception, by the way. They're like, oh, turkey has tryptophan, that's why you get sleepy. Eggs actually have more tryptophan by mass than turkey. So you just get sleepy because you overate, all right? Don't blame the tryptophan, all right? Okay. So yeah, particle speed increases, collision rate increases. And so therefore, effusion rate increases. Okay, what about temperature of the gas? Does collision rate, how does that change? Increase, yes, because temperature increases, speed increases, the particles collide more, right? Yeah, so then we'll see a higher effusion rate. All right, which has a higher collision rate, a heavy particle or a light particle? Light particle, yes, and again, it all comes from the RMS speed equation, which we already know. So just take the extra step and relate collision rate to effusion, rate of effusion, and then relate that to your RMS speed. All of that is there. So yes, fusion rate, collisions with a pinhole increases with temperature, decreases with molar mass. Great. All right, so the RMS speed gives us the trends, but we can actually plug in some values to calculate some actual effusion rates. But the only way that we do it is through Graham's law, where we actually compare the ratio of effusion rates of two different molecules typically with different masses. So we're assuming that these two substances, these two molecules are at the same temperature. So all we do is compare their molar masses. So what we see is that the rate of one substance over the rate of the other substance is equal to the molar mass of substance B over A. So it's rate of A over B equals square root of molar mass of B over A. So note that it's like opposite, right, on the different sides of the equation here, because this allows us to relate, oh, okay, the heavier the particle, the slower the effusion rate. So that's how we get that there. All right, and so you can see here like a nitrogen balloon and a helium balloon. Which substance is heavier, nitrogen or helium? Look at the periodic table. Nitrogen's heavier, so it's going to have a slower effusion rate. So it's going to effuse slower, that it's going to take more time for it to empty. That's what I have here. How is effusion rate related to time it takes to completely empty? As the rate increases, time to empty decreases. So that means the helium balloon is actually going to deflate faster because its effusion rate is faster. Its effusion rate is related to the light molar mass of helium. So which balloon has the higher rate of effusion? In this case, it would be helium because it's lighter, okay, lighter molar mass. Which balloon takes longer to effuse? It would be N2 because it has a smaller effusion rate, that's moving slower, all right? To relate this into something you've actually maybe seen and experienced, and to add my commentary, if you haven't noticed, I'm very cheap, real cheap. Over break, I changed all of the spark plugs and ignition coils in my car because I refused to pay someone to do it, right? Okay, so I'm very cheap. So if you've ever gone to a party, right, and they buy helium balloons, you buy helium balloons, right? But I'm cheap, so when I buy helium balloons, I also blow up balloons like with my lungs also. So the party like looks more festive, but I don't pay more money because helium is expensive, right? Yes, so half helium balloons, half normie balloons with like lung air. So if you've ever gone to a party where maybe they've done this, have you ever noticed like if you're in part of the cleanup crew the next day for the party, all the helium balloons are real small and all of the balloons that you blew up with your free lung air, they stay big. You ever notice that? Never know? Well, next time you are part of your party cleanup crew, do take note of that the helium balloons that you pay money for, they don't last as long because their effusion rate is faster, their molar masses are lighter, so then they collide more, and so the effusion rate through a pinhole happens much faster. Like what we see here, that the helium balloon deflates sooner because it has a faster effusion rate, and you see that at parties, although, you know, the aftermath of a party. All those helium balloons are all shrunk, right? I can just see dollar signs like going in the trash can, and all of the balloons that I filled up with my lung air, like if you think of the air we breathe, it's like oxygen, you know, CO2, nitrogen, much, much heavier than helium, so the effusion rate is slower. See, you've experienced it. Don't pretend you don't. Okay. All right, so that's effusion rate. Let's do an actual question now. All right, so we have a tank. It contains equal moles of HF and HBr gases. It develops a pinhole leak. I'm even nice. I give you the molar masses of those. So which one effuses faster, HF or HBr? HF, yes, because it is lighter, yes. Of those two, which one empties first? HF, yes, because it effuses faster. Okay, good. All right. All right. Will HF effuse 2 times faster or 4 times faster than HBr? So in this instance, we actually need to calculate it, or we need to use Graham's law. We only just use the trends, you know, molar mass, temperature, all those things. So let's actually calculate the rate of effusion of HF over HBr. So when we do that, we compare their molar masses. Whoops, right? Yeah, we compare their molar masses. Which one goes up top? HBr. So the HBr is about 80 grams per mole. HF is 20 grams per mole. So you see the ratio of molar masses is about 4, but I missed something here, the square root. So can you answer the question now? How much faster does HF diffuse? Times 2 or times 4? Times 2, yes, because if you forget the square root, you'll say times 4, but don't forget the square root. All right, good? Okay. All right, so that's Graham's law. Right, and you can just imagine we just looked at the ratio, but if I could give you just 3 unknowns, 3 of these unknowns, and you could calculate the molar mass of like an unknown, or sorry, I could give you 3 of the variables and you calculate one of the unknowns. That would be a pretty straightforward just math question. All right. Okay. So, all right, let's finish this up. All right, so we'll go on to the last part of this chapter, and that's real gases. So I'm going to bring up this molar volume graph again. When we were exploring PV equals nRT, we saw at STP, like a lot of these gases actually have the same molar volume. That when there's 1 mole of nitrogen gas, helium, hydrogen gas, they're all basically 22.4 liters at STP conditions. That's our ideal gas volume, all right? Basically, all of those values, you put in 1 mole, you plug it into the ideal gas law equation, and what we see is that the volume that comes out matches the ideal gas law. What we see here are these middle substances, chlorine, CO2. They're not that close to the ideal gas law. So when we actually put a mole's worth of chlorine in a container at STP, it actually does not occupy 22.4. So there's something else going on here, and that's the idea of real gases. Not everything fits the perfect mold of the ideal gas law equation, PV equals nRT. We consider that idealized, all right, where everything follows kinetic molecular theory. So we'll look at some examples where kinetic molecular theory actually breaks down, and I hope I can make it obvious of when do we need to consider real gases, what factors do we consider, when can we consider things ideal gases. For the most part, we consider things ideal unless we specifically state, hey, consider this a real gas. Then we need to think about what causes these changes. So we're basically looking at, okay, most of the times things follow PV equals nRT, but because we're in college and we look at the weird exceptions, we will look into the weird exceptions of these two right here. All right, and that considers real gases, where when we're on Earth, typically, for the most part, gases behave ideally. And that's the trick I use to memorize when I have to consider real gases. Because gases deviate from ideal behavior at high pressure and low temperature. That's the opposite of earthly conditions. Earthly conditions is 1 atmosphere, that's fairly low pressure, and we are at fairly high temperature. 298 Kelvin is really high comparatively. So that means everything that's not earthly conditions is non-ideal behavior. So that's high pressure, low temperature. The reason we consider these two scenarios is because the two of the postulates of kinetic molecular theory break down. And I'll go into more detail in a little bit, but basically at high pressure, real gases have molecules that occupy some volume of your container. That's postulate 2. In kinetic molecular theory, ideal gas law, we assumed that gases don't take up space, right? It's like all the space is the container. So with real gases, we actually consider the space that molecules take up. That happens at high pressure. Real gases may attract one another to some extent. That's postulate 3. We assumed all of the collisions were elastic, that there was no, basically 2 molecules collide, there's no energy lost at all. We made that assumption in KMT. We can't do that anymore with real gases, all right? And so in order to account for these 2 postulates being kind of voided, we use the van der Waals equation. Don't be scared by this equation. Yes, there's a lot of terms, but I like to just think of it, it's the ideal gas law with some spinach on it, all right? There's just some spinach on it. I'll show you. Okay, so here is my P term. In this big parentheses, there's my P term with some junk next to it. Okay, that whole parentheses is my P term. The next term, there's my V term. And I'm just putting some sprinkles on it to adjust it for the postulates we're now considering. Equals nRT is the exact same. So it's basically pressure with some stuff on it, volume with some stuff on it equals nRT. And so we typically have to give you A and B, but what we learn in this course is, okay, what is the significance of these A and B terms? So this is how we account for the breaking of postulates 2 and 3. A is related to particle attractions. The B term is related to particle size. Right, and we'll see their significance here in the equations. Yeah, so this is dependent. A and B will change depending on what your gas sample is, and there's different numbers there. So I want to show you some kind of like examples of real gases. Remember, non-ideal conditions, high pressure or low temperature. So in this first graph, it's kind of showcasing and proving to you that gases don't behave ideally at high pressure. So the x-axis here is pressure. So over here we have really high pressure. Close to the zero axis we have low pressure, close to zero. So like earthly conditions, 1 atm is like right here on the graph. So what you want to focus on is that when any of these colored lines fall on this straight ideal gas line, that means that the ideal gas law equation can explain that system, those temperature or that pressure system here. So when we see any of these lines deviate at all from this horizontal line, that means we have to use the van der Waals equation, that the ideal gas law cannot describe anything where it's all curved like that. And most of this happens, the lines basically deviate the most from that horizontal line at high pressures. That's what I want to show you. And that kind of proves to you that at high pressure, we have non-ideal conditions. We need to use the van der Waals equation. Over here, it's a very similar graph. We still have pressure along the x-axis. And again, an ideal gas will fall exactly on this horizontal line. So what we see here is this is the same sample, just at different temperatures. So we see that at low temperature, the lines deviate the most from ideal behavior, but as we heat up the sample, that it starts to resemble, it will become more straight, more horizontal, that at 1,000 Kelvin, there's tons of kinetic energy there, really high temperature. This line is the closest to ideal at all pressures versus at low temperature. So that's kind of, again, proving to you our non-ideal conditions, high pressure, low temperature, but conversely, if we have a sample at low pressure, high temperature, we can usually use the ideal gas equation just fine because it falls in this low pressure region that falls on that ideal gas line. So that's kind of just proving it to you. So we mentioned, I mentioned the A and B terms in the van der Waals equation. So what are they? So these are just literature values for the A and B terms. If you have to do a calculation like on online homework, know that you can just look up these values. Or if you need to use the van der Waals equation to calculate pressure, you just have to look up these values. On an exam, if we want you to calculate something, we would have to give you these values. So what I want you to see is that these A terms, remember, is related to attractions, and we'll talk more about that in chapter 11. The B term is size, related to size. All right, so we see as the molar mass increases for these substances, the B term obviously increases. Heavier molecules, larger B term. We haven't talked about attractions yet, that's in chapter 11, but the general trend I want you to see here is right here. As the B term increases, the A term usually also increases. So that's a general trend that will help us here, and we'll talk about why in chapter 11. But yeah, as B increases, usually we see A increase too. And so when A and B, when those terms are large, usually your sample will deviate from ideal conditions more. That when A and B are large, it is more important that we use the van der Waals equation, all right? Because their significance when we're adding or subtracting them in the equation, it becomes significant. So those are the A and B terms. Okay, so how does the A and B terms actually change? Remember the van der Waals equation. We have the P term and some spinach times the V term and some spinach equals nRT. So let's explain, okay, what are those small like adjustments we make? That's what I mean by the spinach. This is where it comes into play. So at high pressure, the B term becomes very important. Why? In order to make something high pressure, like if I have a tank of gas, all right, and all I can do is put more gas into it, how do I increase the pressure in the gas tank? You do what? You have to add more gas, right? So if I want a really, really high pressure, I have to have a lot of gas particles in the container, to the point where if you add so much gas to increase the pressure, there's so many gas particles in a small space. Now, if we're considering the size of each of those particles, if you have to shove a bunch of particles in that space, you have to actually think about, okay, those particles will occupy some space of the container, all right? Each of those particles, because there's so many particles in there, actually take up some space. And when that happens, the overall gas system has less volume to bounce around. And so that's what we have down here. All right. The volume in which the molecules are free to move is slightly less than the volume of the container, because we're subtracting the amount of space the particles actually occupy. All right. So the volume the gas freely occupies equals the actual volume of the container, but now we're taking into account the size of the particles taking up some of that space. So that minus NB, that's the little sprinkles we have to add. All we're doing is taking into account the size of the particles, all right? And so you can see, as B increases, if B is a big significant number, right, then we're actually changing the volume of the gas freely occupies, it's significant. Or if we have to shove a ton of moles of gas in a space, we are subtracting a fairly large number. And that's when these two V values will be different. That's why we have to use the van der Waals equation, all right? So that's the B term. I feel like people usually get that one. That's why I show it first. Has to just do with size of particles. We can no longer pretend like gas particles are just invisible, like nothings. We have to actually consider their size. All right. The next one is at low temperature. All right. Low temperature, this is where the A term dominates. A stands for attractions. So the idea here is, before, we thought of gas particles as these like chaotic billiard balls that were just bouncing off one another, complete elastic collisions. They were, like it was like a physics problem, right? Where there was like no external factors, okay? But the thing is that these particles, depending on the identity, actually don't have elastic collisions. Sometimes when two particles come together, if there's significant attractions, I like to think of the particles, they're sticky, right? So if two gas particles come together and they're highly attracted towards one another, they will still bounce off from one another, but just for a split second, they will be attracted towards one another. They'll stick to one another before bouncing off away from one another. That's how I like to think about it. So when we have low temperature, that means there's low kinetic energy, that the collisions are already low in energy. All right, low elastic or like low energy collisions. So if there's any amount of stickiness, okay, on that collision, then a lot of the that kinetic energy is lost. So I like to think at low temperature, the attractions and the stickiness of the particles towards one another dominates, and the particles bounce less on the sides of the container. So if the particles are sticking to one another, they're hugging one another, are they going to collide with the walls of the container more or less if they're sticking towards one another? Less, yes, and that's what this equation is trying to say. When the attractions of the particles are large, they're hugging one another, so they will collide with the walls of the container less. So will the pressure be higher or lower than ideal? Lower, yeah, because they're sticking to one another. They're not bouncing off the walls and like colliding. So you you measure a lower temperature than normal. So that's what this is trying to do, that your ideal pressure is your measured temperature plus this attractions term. The more attracted your particles are to one another, the less elastic the collisions, that you're losing a lot of energy because they're sticking towards one another, so they're not going to hit the walls of the container as much. And then this is what we insert into basically the ideal gas law, all right? And that's what I mean. The van der Waals equation is just the ideal gas law with some sprinkles on it, where we account for attractive forces through the A term. We account for the size of the particles. That's the B term. Okay, all right, so there we go. All All right, that's how we get the van der Waals equation. It's like the exact same thing. So these adjustments that we make dominate when we're at high pressures, because basically you have to shove a ton of moles of stuff into the space, or at low temperatures. And again, because of the attractions thing, and it's just conservation of kinetic energy. All right, so hopefully when you squint your eyes, do you see the ideal gas law equation here? When you squint your eyes, I don't want you to be scared of this equation. I want you to think about this equation in terms of the ideal gas law, but we just consider some of the postulates that we, have to consider. Size of particles and attractions. If you squint your eyes, hopefully you can see the ideal gas law. So with that in mind, we can actually calculate the pressure using the ideal gas law and the van der Waals equation. And that's what we're going to do on the last two slides, okay? That given this information about a sample of CO2, let's calculate the pressure using the ideal gas law. This is straightforward. This is plug and chug. It's PV equals nRT. You could do this all day. But the harder one is the second one. It's, okay, let's calculate the pressure according to non-ideal behavior. So this is where we use the van der Waals equation. It's tedious, so let's just do it. All right, so let's go through the information that I give you. So let's calculate the pressure exerted by 1 mole of CO2. So what variable is that? Let's be in the science mode. What variable is that? N, yay. Okay, N. 1 liter tank, that's V. 298, that's T. Great. I didn't even give you in Celsius, so we don't even have to convert things. So we can see using the ideal gas law, so the first part here, we just plug it into Pivnert and solve for pressure. So using the ideal gas law, P equals nRT over V. So I just plug that in. 1 mole, R is 0.08206 liter. ATM, mole Kelvin. Temperature, I already give us 298. Over volume, so what is it, 1 liter. Okay, equals, I already have it down there, 24.4 ATM. Good. You could do that all day? Yes. Okay. It's the next one is tedious. We use all the same information, but we have to now include the A and the B term for CO2. So if this was a mastering question, you may have to look up the A and B term for that specific substance. If it was like CO2 or like helium or something, you would use different A and B numbers. So to do the real gas with the van der Waals equation, it's just tedious. We're still solving for pressure. I just do it in a way where I don't mess up my arithmetic. So I'm going to basically plug everything in and solve for P here. So let's just do that. So we're solving for pressure, plus I'm going to drop units because I'm lazy. N, so N squared, so that's 1 squared, times the A term, so 3.59, over volume squared, just so don't forget those squared values. Volume is what? 1. Wow, that's nice. I even gave really easy numbers, and it's still tedious. Times, again, another parenthesis, volume, so 1 liter minus N times B. So N is 1 mole times that B value is 0.0427. Boop. Okay. Equals nRT. So it's all the same stuff as before. So 1 mole times R times 298. Okay. Right. So what I like to do is actually like do the arithmetic here. So pressure plus 3.59. I do the arithmetic in the parentheses. So this new term, so this new volume is, so look, I'm taking 1 liter and subtracting how much space a mole's worth of this gas particle occupies. So I think that number is 0.9573 liters. So essentially, you can put a mole's worth of CO2 in a 1 liter container, but the amount of free space they have to bounce around is actually 5% lower because of the size of the particles themselves. All right, equals nRT. So that number I think is like, 24.45 or something. All right, so if you divide both sides by 0.957, you get something like pressure plus 3.59 equals, I think it's like 25 point something. 24.45 divided by, oh, I already have it here, 25.54. All right, and so when you subtract 3.59, you get pressure here. You finally isolate pressure. So you don't have to like distribute anything, just carry over that arithmetic. You get something like that the pressure is about 22 atmospheres when you consider CO2 to be a real gas. That's really significant. Yeah, if we plug in the known numbers into the ideal gas law, we get 24.4. But if you consider, the breakdown of some of the postulates, the van der Waals equation does give a much different number. So that is it's nothing to sneeze at, all right? It's pretty significant here, the difference. All right, I don't know about you, but the real gas law, the van der Waals equation, it's tedious. It's tedious, and I even gave you easy numbers, and I put all of the A's and B's in front of you. So let's do one without any calculations. Oh, I already have the answer there. Let's try not to have the answer. Okay, let's try not to have the answer there. All right, so no calculations. Okay, so we have two identical containers. They're at the same temperature. Each container, one contains a mole of nitrogen gas, the other one contains a mole of CO, carbon monoxide. Both molecules are relatively the same size. Actually, if you calculate it, both of them have the exact same molar mass. I think both of them are 28 grams per mole. So they're, I don't want to say it. Okay, so they're the same size. But if we consider N2 and CO to be real gases, which one will you predict to have the higher measured pressure? The canister of N2 or CO? Real gases. So remember, what terms do we add to the ideal gas law when we think about real gases? We have the A and B term. Because if you just use this information and plugged 1 mole into the ideal gas law equation, shouldn't both of those containers have the exact same pressure? They should be the exact same if we plug them into in PV equals nRT. But we're considering these to be real gases. So remember, real gas, A and B. So when I say that the molecules are relatively the same size, N2 and CO, what term am I referring to? B. Okay, so the same size. So I can ignore B. I ignore the B term because they're the same number, right? So we can't differentiate on that. So what can we differentiate on? The A term. So compare their A's. So you might need to think of, so what does A stand for? Attractions. Yeah, so I briefly said that when B increases, A usually increases. But there's actually other factors as well. Think about other attractions. All right? Nitrogen, diatomic nitrogen is what kind of molecule? Will it respond in a magnetic or electric field? No, because it is nonpolar. But what about CO? It is polar. So which one, just use your intuition here, which one do you think has a larger A term? CO, yes, has the larger A term. Yay. So more attractions with CO in our CO sample. Is that the answer to my question? No, it's not. I'm asking you which container exerts the higher pressure. So think about it. How is an increased A term for CO, how's that going to adjust your pressure from ideal conditions? Is it going to make it bigger or smaller? So remember, A means attractions to the particles themselves, that the sample is more attracted to itself. So is it applying pressure on the walls of the container? No. So CO is actually going to have a slightly lower pressure. N2, because it's nonpolar, less attractions, is actually going to have a higher pressure. Did you see that train of thought? Which one's harder, this one or the previous one? Most people say this one. This one's harder because it makes you think. Yes. So yeah, which one has the higher measure pressure? It's N2. Yes. And it's because CO has more attraction. CO is an overall polar molecule. CO particles, the sample, it's hugging itself. It's not applying pressure. It's not colliding with the walls of the container. That's how I like to think of it, and it works. So yeah. Right. Good. Would you rather this one or this one? This one. Yeah. Everyone loves numbers. But I will point out, so the final exam is like 50, 53 questions. So like we can't have really math extensive questions for all of them. So, you know, if we're going to ask a van der Waals equation or like a van der Waals concept, it's going to be this one. One, it requires you to know your stuff. Two, it's faster to answer because it's not like number crunching. It's not number crunching. You actually need to know your stuff here. While on this one, yeah, you can just plug in the numbers, but you can have no idea what you're doing, right? Or you might know what you're doing, put it in, and get the wrong answer because of the math or something. And so, yeah, conceptual questions. I know you guys hate it, but we need it. Okay, good. All right, so we're moving on. So that means we're done with chapter 10. Homework is due on Sunday. Okay. All right, so let's go to chapter 11. All right. Okay, so how many of you here are taking 1220? Okay, basically all of you. All right, so I'm going to tell you, chapter 11 and 12 are the most important chapters to ensure your success at the beginning of 1220, because we hit the ground running in 1220 and we assume you know all this stuff. So I'm going to do my job here and make sure you know all your stuff. But what sucks is that I have less time to cover 3 chapters, right? So I have most of the blanks in here for you. Yeah, okay. So the topics and like skills you really need to know for chapters 11 and 12. So liquids and solids. So I don't know if you've noticed, but chapter 10, we did gases. Now we're doing liquids. Chapter 12 is solids. So we're working our way up. We're using all of the skills we've kind of gained along the way here. They're all coming back. So I want you to review Lewis structures, molecular geometry, and polarity. I want you to be able to look at a formula, a molecular formula, and tell me, is it polar or not? And that's an important skill, all right? And that's going to come back into play when we talk about intermolecular forces. A lot of it comes down to polarity. Yeah, and so this will come back in chapter 12, next chapter, and be really important in 1220. Okay, so we will look at the differences between gases, liquids, solids, what properties kind of dictate that. I don't know if you've ever noticed, like why, like we breathe oxygen, right? We have to breathe, to live, we need to breathe oxygen, and oxygen's a gas. And basically how humans, how our bodies are designed, right, is based upon the idea that oxygen's a gas. Why is oxygen a gas? I don't know. What about water? Water on Earth is a liquid. Have you ever thought about why is water a liquid? Why have we evolved to understand, use water in its liquid form to nourish us? You never thought about that? You have thought about that. Okay, well, we will learn about that, all right? And the factors that explain why things, what properties or physical phases things are at room temperature and pressure. Because, as humans, we are selfish. So we think about, what is the phase of water at room temperature? It's a liquid. But, if we were on another planet, all right, where it's real cold, water might be a solid. And that's its typical thing there. So these are the things we'll look at. What factors dictate that? And the moral of the story, it's intermolecular forces, and we'll look into see how do those forces, those attractions between particles, explain other properties. So this is a very important chapter that explains, why things are the way they are, and it comes back to the idea the secret to chemistry I mentioned. It's composition and structure that dictates chemical properties we see. And so we're looking into the structure part, and that becomes important here. All right. So states of matter. We already talked about gases. So now we're on liquids and solids. So the true reason why oxygen's a gas on Earth, why water is a liquid on Earth, why, salt, like rock salt, why it's a solid at room temperature, has to do with, I know you hate it, the balance between kinetic energy and potential energy, right? So it's those ideas are coming back. Kinetic energy, we've already described, is related to the temperature of the sample. So all of the kinetic energy of your particles related to the temperature of that sample. So temperature, very important to tell us how much kinetic energy is available to my sample. That is being balanced and kind of competing with potential energy of your sample. Potential energy comes from attractive forces. So remember our favorite, right? Potential energy curve. When we talk about the top and the bottom, what kind of forces are at the top? Repulsion, yeah, so plus plus or minus minus, right? But the bottom one, and this is the one we care more about, is the attraction. So just two oppositely charged things, all right? So we get potential energy coming from attractions of particles towards one another, and that is balancing with or competing with the kinetic energy of the sample. Attractions keep particles close together. Because if we think about it, if you were two particles that are attracted towards one another, and if you're like a ball rolling on this graph, if nothing was there to stop you, which way will the ball roll? Down. And if the ball rolls down, will the particles get further or closer together? Closer, yeah. So its attractions are keeping things together, kind of like in the solid phase. Well, while that's being counter or competing with the temperature of the sample, all right? So these are the two things we want to be thinking about. All right, so let's look at an example here. It's a great series, chlorine gas, diatomic chlorine, diatomic bromine, diatomic iodine. All of these are halogens, diatomic halogens. They're all group 7A, right? We just go down the group. All right, so what's really cool about this series is that diatomic chlorine on Earth, like if I just pulled it off the shelf, chlorine is a gas. It's a gas. But if I just go down a group and I pull bromine off the shelf, it's a liquid. If I pull iodine off the shelf, it is like at room temperature and pressure, it's a solid. So we see a major difference in boiling point and melting point data here, and this is related to the balance of kinetic energy and potential energy. Remember, kinetic energy comes from temperature. At room temperature, all of these samples have the same kinetic energy, but what differs is the attractions between particles of these samples. So we already talked about this in chapter 1. The ideas of the packing and motion between gases, liquids, and solids, right? The motions of the gas particles, they're moving freely, kinetic molecular theory. So if we think about it, if we compare kinetic energy and attractions, which I just call intermolecular forces, okay? So just think of attractions. Which dominates in the gas phase? Kinetic energy or particle attractions? Kinetic energy, yes, because they're moving like chaotic children, all right? Those gas particles, they're moving around, tons of energy, tons of excess kinetic energy, right? Versus the solid. So let's think about the particles, description of a solid. Less movement. There's not no movement. There's still vibrational movement, but packed, highly ordered. So what do you think dominates in the solid phase? Kinetic energy or the attractions from intermolecular forces? Attractions, yes, because all of those particles are packed. And then in the middle here, liquids are actually, the kinetic energy and intermolecular forces are on the same order. They're about the same value. They're still packed, so there's still intermolecular forces keeping it together, but not enough to stop translational motion. All right, so that's what we want to think about. And when we think about it, yeah, when we want to boil something, we increase the temperature. But when we do that, we're increasing the temperature to increase kinetic energy to overcome intermolecular forces. All right, so that's basically what describes all of the properties that we will discuss this chapter. Intermolecular forces is very closely tied to boiling point data. All right, so kind of to relate this to something in chapter 10, we just talked about the A and B terms, right? B is size, A is attractions. This is the same attractions I mentioned. You know, we're going to learn about IMF's attractions in chapter 11. We said typically when size would increase, the B term increased, we saw a larger A term. And that's correct for like 90% of the data. So if I took all this data and I graphed it, I would see that most of the data follows that trend. As B increases, A increases. They fall on that line, where I have B on the y-axis, A on the x-axis. But what's weird is that water, H2, actually doesn't fall on that line. It actually has, water has more attractions, right? Because it's fairly light, right? It's kind of where it is on this B, the y-axis is over here. So water actually exhibits more attractions than typical. So this is where we need to use all of the different intermolecular forces to explain this. That size is not the only determining factor for intermolecular forces and attractions. It is one that we can use, but it's not the only one. So yeah, we'll see the explanation of intermolecular forces that explains why water is so weird coming up here. All right, so this next slide, there's a lot of things on here. So I'll just leave that up there. Okay, so I've been mentioning, when I say molecule attractions and intermolecular forces, I mean the exact same thing. They're the exact same thing. Right? So when we have like condensed phase samples, liquids, solids, some type of attraction is holding it together. And there's different kinds we can discuss here. So in general, just like the general definition of intermolecular force is an electrostatic attraction. What do I mean by electrostatic? I mean this, the same potential energy. We have charges, they're coming together, attractions, monkey brain, attractions. But the detail here is that to make an electrostatic attraction, there's actually a bunch of ways we can do it. We can have full-blown charges. So like sodium, we could have like sodium plus and chloride minus. That's technically an attractive force, all right? We already called that something. We called that what? What's the energy involved when we bring a sodium plus and a chloride together? Lattice energy, yes. It is lattice energy. Yeah, so we can have electrostatic attractions through lattice energy. That's full-blown charges. Those are ions. But we can also have electrostatic attractions between partial charges as well. When did we talk about partial charges? Bond dipoles, molecule polarity. So the idea here is you can have electrostatic attractions between full charges, like in lattice energy, we already talked about that, but we can also have attractions with things that are polar because they have partial charges. So like a partial positive and a partial negative, they're still going to be attracted to each other, just not as much as, you know, full-blown charges. So here's an example of a intermolecular force. See how it says it's weak? All right, so these interactions between partial charges is quite weak, not like our lattice energies that were really strong. So here we have two HCl molecules. If you inspect their differences in electronegativities, the hydrogens are more electropositive. So basically what's happening here is that a hydrogen on one molecule will be attracted to the negative end of another molecule, a neighboring molecule. So inter means between molecules. So that's the big distinction here. IMFs, all of this chapter 11, are attractions and interactions between different molecules in a sample. So like here, we have two HCl molecules, two of them. We need to have two of them. Don't mix this up with covalent bonds. That was in chapter 8 and 9. We talked about covalent bonds and electrons forever. Covalent bonds are between atoms that build a molecule. So for example, in HCl, they even point here, the HCl covalent bond, that's a really strong bond. We're not breaking those in this chapter. We've already built covalent molecules. What we are now focusing on are interactions between neighboring molecules. So that's the big distinction here. We don't care about the covalent bonds. We're actually looking at weak bonds between molecules. Okay, there we go. So of these IMFs, and that's what we're focusing on, the attractions, there's 4 we're going to talk about today, and we're going to talk about them in order of increasing strength, or sorry, weakest to strongest. So the first one here, London dispersion, or just dispersion forces, and I have here what to look for, and I will explain each of these, all right, and the trends that we typically look for, and how we can't measure the magnitude of IMFs in a sample. So just again, think IMFs is attractions. So the first one of the 4 that we're going to do, so the first one is London dispersion forces. This one's the weakest. All matter exhibits London dispersion, but it's most important for nonpolar substances because nonpolar substances only have LDF present. And so I'll tell you the trend, and then I'll explain all the trends. So LDF, which is just, a type of weak attraction, it increases with increased molar mass of your sample, and it increases with increased surface area. Molar mass is more important here. Molar mass is more important, okay? Okay, so, and I mentioned that this intermolecular force is the most important in nonpolar substances. So let's think about it. If we have 2, let's say nonpolar atoms, 2 helium atoms, are they polar? No, they're just like neutral, right? So like in your mind, intermolecular forces are electrostatic attractions. So hopefully your brain is confused right now thinking, where are the electrostatic attractions coming from helium? It's just a neutral atom. And you should be confused, okay? That's why this one's really weak. So helium atoms, when we think of 2 helium atoms, they're neutral, right? There's no electrostatic, there's no bond dipole at all. It's just an atom. So this attraction actually, oh, it's all messed up. That's all messed up. There we go. So what's happening here is we're producing, helium can produce what we call a temporary dipole. Temporary. That's why this is very, very weak. If we produce a temporary dipole, we can induce another dipole on another molecule, and just for a split second in time, those 2 atoms can be attracted towards one another. That should make no sense to you right now. So I'm going to describe it step by step. Okay. How many electrons are on a helium atom? 2. Do those electrons stay in one place on the atom, or are they zipping around like crazy? They're zipping around, right? Because if they were in one place, we'd violate what rule? Heisenberg's uncertainty principle. You guys are smarter than you think. Yeah, okay, so they're zipping around. That's what I want you to be thinking about. So if they're zipping around and you take a picture of them, like where those electrons are, so then we would violate the uncertainty principle. But if you take a picture of them, there's like statistically like a billion different arrangements where those 2 electrons can be, right? Right? So like if you take a picture of them and you have 1 electron over here, 1 electron over here, that negative charge is kind of, placed evenly, smeared evenly around the atom. But let's say you take a picture at another moment of time and you get this picture. Maybe you take a picture of the electrons and they're both on one side of the molecule, just for a moment. So just for a moment. So these electrons are negatively charged. What's this black dot? That's the nucleus. What charges the nucleus? Positive, yeah. So we have a partial positive over here, and where those electrons are, we have a partial negative on the other side. So if you're an electron on another atom, and you're looking at the other atom, are you gravitated towards one part of the molecule more than the other? Yeah, you're a stupid little electron. You're gonna be attracted to the partial positive side, right? That is a temporary instantaneous dipole, meaning that it happens for a split second, right? Just a split second. These two electrons just happen to be on another side of the molecule where it induces a dipole in another atom. Sorry, another, like electrons on another molecule, where this electron is slightly attracted to that side. And that's what this last picture is saying. So this only happens for a split second, and then it goes away. But then it can happen to another neighboring molecule, induce another dipole, and then do that again. All right. So these are all temporary dipoles. It's the only type of attraction for non-polar compounds. So this phenomena happens more if there are more electrons present. Right? Like if you just think of statistics, if there's more electrons, there's a greater chance you could have some of the electrons congregate on one side of the atom or one side of the molecule more than another. So that's where this trend comes from. That as molar mass of your molecule or atom increases, typically you think, oh, more protons, right? But as you increase the number of protons, you also increase the number of electrons. So more molar mass means more electrons, means a higher chance of inducing temporary dipoles. That's it. And that's where London dispersion comes from. Cool? Yeah, temporary dipoles, super weak, super weak. If there's any other intermolecular force present, like the second, third, fourth one that we talk about, usually that dominates. Okay. Okay, so why does this happen? It's because electrons typically are polarizable. Polarizable just means electrons that are able to distort their electron cloud. So if it can distort, if the electron cloud can distort, then you can induce a temporary dipole easily. If it's very polarizable, you can induce a temporary dipole, meaning London dispersion forces is stronger, increases there. So the aspects, the things that affect polarizability, and this is a concept that's important in organic chemistry if you have to take it, so keep that in your back pocket. Being able to distort an electron cloud also relates to reactivity. So polarizability and London dispersion forces. Polarizability being able to, I like to think of like a big jello, like you got a big jello thing, and if it's like big, then you can like slap it and like the jello wiggles, you can distort that electron cloud, right? When it's nice, big, fat, and juicy. So the idea of polarizability where that can increase is if the weight of the molecule increases, polarizability increases, therefore London dispersion forces increase, all right? And one we didn't talk about yet is surface area. When the weights are similar, oftentimes we will look at surface area of the molecule. So as surface area increases, we see LDF also increase. So linear molecules have actually high surface area. Spherical molecules have low surface area. So this example we see with surface area, N-pentane is more linear, is actually more polarizable because there's more surface area, more interactions for electrons to like induce a dipole in one another. So we actually see a higher boiling point temperature because there's more LDF present. And neopentane is like more compact, more spherical. It has a lower boiling point temperature because there's less surface area. And if you look here, they actually have the exact same weights. They're isomers. They're the same formula there. So that's why we have to look at surface area for these two molecules because their weights are the same. But usually weight is the find factor for us to look at increasing London dispersion forces, where we basically just look at the molar mass. So if we bring back up chlorine, bromine, iodine, we clearly see molar mass increases as we go down the group. And so what we see is boiling point temperature increase, and that's indicative of more intermolecular forces present, more attractions. So I have to give the sample more energy to break apart into the gas phase. And so remember, chlorine is a gas at room temperature because it has weak attractions. That just room temperature is enough kinetic energy to send it into the gas phase. Versus iodine, really, really heavy, strong IMFs, so room temperature is not enough kinetic energy to send it into the gas phase. So that's where these ideas and these properties, observations we make, why it's so important to understand where attractions are coming from. So this series purely uses LDF because they're all nonpolar. They're all nonpolar. Okay. All right. So let's look at more data. Great. The big idea here, as intermolecular forces of your sample increases, we see an increase in boiling point temperature. Why? Let's think about it. When we boil water, boiling water, we turn a liquid to a gas. Boiling is what kind of change? Physical or chemical? Physical. Okay, good. So then you can answer this question. When we boil something, what are we breaking? Covalent bonds or IMFs? IMFs, because you just told me it's not a chemical change. If it was a chemical change, we'd break covalent bonds, right? But it's not a chemical change. It's physical, so all we do is break IMFs. So the idea is, if there's more attractions to the particles, they're hugging each other real tight. So you got to give them a lot of temperature, a lot of kinetic energy to rip them apart. All right, rip those suckers apart. So more IMFs, more attractions, you got to give it more kinetic energy, higher boiling point temperature to rip all of those particles apart, but not the covalent bonds, just the attractions between them. So we can see that in this data, as we increase the molar mass, as we go down the group of a lot of these molecules, the boiling point temperature increases. So neon, argon, krypton, xenon, we see like a real nice increase in boiling point data because the atoms are getting heavier. London dispersion is increasing, takes more energy to send those gases, those atoms into the gas phase. We see the same thing with the halogen series, diatomic fluorine, chlorine, bromine, iodine. It also increases very nicely going down the group. So molar mass increase explain these two phenomena, this one and that one separately. We already talked about shape of molecules. It affects the strength of dispersion. Our long, skinny molecules have more surface area, so more London dispersion versus our compact molecules. We usually look at surface area if molar masses are the same. Okay. So with that in mind, LDF London dispersion can either be explained by molar mass or surface area. All right, so let's look at this data. Let's compare the boiling point temperature of chlorine. So it's right here. That's the boiling point temperature of chlorine versus xenon. It's right here. And I also have it right there. Those are the boiling point data. What explains the difference in boiling point? The molar mass difference or the surface area difference? Think. Surface? Don't just say the first thing on your mind. Check in your brain to see if the trend matches the observations you see. Okay. Yes. So if we look, so let's just go through both of them. Let's say you said molar mass. And let's just predict what how the difference of boiling point data would be and see if it matches. So if it was molar mass, which substance would have the higher boiling point temperature? If the answer is molar mass. Xenon, but does that match what we see? No, it doesn't, so it has to be surface area. But let's check. Which substance has more surface area, a diatomic or a atom? A diatomic. A diatomic actually has like twice as much surface area, almost twice as much as a spherical thing. So diatomic chlorine actually has more surface area, so that is why its boiling point is higher, all right? That its electrons are spread out enough that it's more polarizable and it can do dipoles like we can say with London dispersion. So don't only think of London dispersion as molar mass. That usually gets us most of the way there. Sometimes we do have to consider surface area there, all right? Okay. So yeah, the difference between like this and this is because of surface area, but if we just look at the colored graphs this way, molar mass does us just fine. Okay, there we go. All right, so moral of the story, boiling point and total IMFs does a great job. They're directly related towards one another. So with that in mind, let's look at the boiling point data of these molecules, which, based upon boiling point data, which sample has the most attractions, the most IMFs, based on boiling point data? Acetonitrile, yes, this one has the greatest IMFs. And then which one has the lowest? Propane, yes, because it has the lowest boiling point. Great. All right, let's see how we can't explain this. So you might first think, okay, well, we learned about LDF. That's related to molar mass. Let's look at the molar mass of these things. Does molar mass explain the difference in boiling point? So if we see it increases going left to right, does molar mass explain the boiling point data? If it did, if molar mass did, what would we expect? We would think molar mass would increase going left to right, but we don't see that. They're basically all the same number. So does molar mass explain the difference in boiling point? No, it doesn't. And this is what segues me into the next intermolecular force. If you kept it in the back of your mind, the list. The next one is called dipole-dipole. Do you remember what this symbol is? This one right here. Mu. That's dipole moment. Yeah. So what things exhibit dipole moments? Polar molecules, polar bonds. So things with permanent dipoles have dipole moments, and that's what a dipole-dipole interaction is. So if we look at the dipole moments here, they're the ones that actually increase left to right. We have basically 0 for propane, 1.3 for ether, 2.7, 3.9. So it's dipole-dipole. The dipole moment for these molecules is what's creating this trend. A dipole moment here, remember, we can use like a dipole arrow, and you can think of them like as little magnets. So for propane, there's essentially no dipole arrow. It's just tiny, 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 tiny. Versus for acetonitrile, it's like a huge dipole arrow, all right? A huge dipole arrow that can interact like magnets. There's more attraction towards one another because these dipoles are permanent. They're not instantaneous or temporary like they were in London dispersion. Versus ether and acetaldehyde, they're smaller arrows. So that's why we see slightly lower boiling points there. All right, so that's what this next one is. It's dipole-dipole interactions. So what you need to look for are molecules that have permanent dipoles. All right, polar molecules. So that means you might need to draw the Lewis structure. You might have to draw the Lewis structure to see, okay, do the bond dipoles cancel babies and bodybuilders? You just need to know, is it polar or not? That's basically it. Because polar molecules will always be more attracted towards one another than nonpolar molecules. All right, and so we can see the interactions here. This is acetonitrile. So what is written in red here, those are the attractive dipole-dipole attractions, where the partially negative side of the nitrogen is attracted to the partially positive side of the hydrocarbon on the other side. So these are all attractions, all right, and it's going to keep the attractions of the sample together. So typically we will see higher boiling point data here. So when we boil acetonitrile, we are just breaking these attractions. That's all we're breaking. We're not breaking up the molecule. All right, so yeah, I just like to think, okay, permanent dipoles, more attractions versus our London dispersion. So let's look at some data. Okay, so here's some compounds. I have their molar masses. So let's go through these hopefully quickly and determine, is it polar or nonpolar? F2, polar or nonpolar? Nonpolar. Argon, nonpolar, it's just an atom. HCl, polar. H2S, nonpolar? It's polar. Okay, good. You all looked at me crazy. Yes, it's polar. But I have the Lewis structure up here, right? And I showed that it's bent, because if you didn't draw the Lewis structure, right, and you might have not thought it is bent, then you might accidentally say that it's nonpolar. But you don't do that, right? You don't do that. You draw the Lewis structure correct. Okay, so Again, if you look at the molar masses and the boiling point data, all of these molar masses are really similar to one another, but the boiling point data is quite different. But if you look a little bit closer, you see, okay, the two non-polar substances have much lower boiling points. It's a lot easier to get them into the gas phase. It's a lot easier to rip all of those intermolecular forces, attractions, apart from one another. Versus our polar substances have basically 100-degree boiling points higher, takes a lot more energy, although, you know, there's still gases here, room temperature, but it takes 100 degrees more to get them to boil, to break all of those intermolecular forces because of the nature of them being polar, that they're more attracted towards one another in their respective samples. All right, so let's look at another example here. So we have acetone and butane. So let's look at butane. What IMFs are present? Is London dispersion present in that substance? That's a trick question. Everything has London dispersion. Yes. What about acetone? Does it have London dispersion? Does it have London dispersion? Everything has London dispersion, yes. So let's compare the extent of their London dispersion. When we look at LDF, what factor do we consider? Molar mass. If we compare their molar masses, do they differ in terms of London dispersion? No, they don't. They're basically the same. Basically the same. Let's just say they're the same because they weigh the same. What's next? Dipole-dipole. Does butane exhibit dipole-dipole? No, it does not. It is a hydrocarbon. It's a hydrocarbon. There's carbon-carbon bonds. Those are nonpolar covalent bonds. Carbon-hydrogen bonds, also nonpolar covalent bonds. But what about acetone? Does it exhibit dipole-dipole? Yes, it does. And I tried to make it obvious with the partial charges written there, right? So with those partial charges there, and essentially you can think we have like little bond dipoles, all right, that the like nose of this acetone molecule will be attracted to the butt of another one, all right? And so there's just more attraction, so it just takes more energy to send them off into the gas phase. Versus butane a lot easier because there's no permanent attractions there. That all we have to rely on are our LDF temporary ones. So does our boiling point data match the magnitude of intermolecular forces that we discovered here? Does it match? Yes, it does, because the boiling point of acetone much higher because the presence of dipole-dipole. All right, so that's how, you know, observation relates to structure. Okay, so like I said, boiling point is a really good indication of the extent of intermolecular forces. More intermolecular forces, higher boiling point data. So up until now, we basically said, okay, heavy things, more IMFs, higher boiling point data. That was like LDFs. We did that. Heavy things, higher IMFs because of LDF. So if we look at these graphs where I show group 4A trends, so like group 4A, like carbon, if I attach 4 hydrogens to it, it has this boiling point. If I change carbon with one row down, if I go to silicon, this is also a gas, has a slightly higher boiling point. Germanium with 4 hydrogens, also just slightly higher. So what we see here is that the whole molar mass and LDF relationship and boiling point works really well for group 4A elements. We just see this constant increase as we go down the group. But we have some weird stuff happening with the other groups. So if we look at if we kind of skip over these points, if we look at groups 5A, 6A, and 7A, we see that there is an increase in boiling point and therefore IMF data. But we have some weird stuff for these really light molecules, water, HF, and ammonia, that they have unreasonably high boiling points, meaning they have unreasonably high IMFs present. So this segues me into the third IMF, where we can't use dipole-dipole, we can't use London dispersion to fully explain these 3 anomalous points. Because, you know, as we know, as in college, we always learn the weird exceptions, right? And so this is the weird exception. where these 3 points don't fit the idea of like dipole-dipole and London dispersion data perfectly, but all the other ones do. It's just these 3. So those 3 have a different dominating attractive force, a different IMF, and it's called hydrogen bonding. Okay, so we will look at the criteria for hydrogen bonding. Basically, it's a special case dipole-dipole. All it is a dipole-dipole, but it's just an unreasonably strong one where we have certain criteria, where we have a really electropositive hydrogen. And to get that electropositive hydrogen, we have to attach it to a very electronegative atom. So this is what I want you to look for, and this is what I want you to write down, is that hydrogen bonding will occur when we have hydrogen attached to oxygen, or hydrogen attached to nitrogen, or hydrogen attached to fluorine, and the very electronegative atom needs to have a lone pair. So that's the criteria that I want you to write down. Hydrogen bonding is super strong. Okay, it's what keeps our DNA together, right? We unzip it, so it's strong enough to keep the DNA together, but it's not strong enough where, you know, RNA can't come in and like unzip it, right? So you kind of have this like special happy medium there. All right, so it is very strong. All right, so I just want you to write that down, and we'll pick up here on Wednesday. We will probably finish chapter 11 on Wednesday. But these homework assignments are real short. They're like 45 minutes long. Yeah.